Hello everyone, welcome back to our class. Let's continue study chapter 5, finite time thermodynamics. Section 2, irreversible processes and work loss. As we know, the actual useful work exported by system always is smaller than that of theoretical possible export work. The reason is that internal and external losses will be produced by various many factors. Generally, external loss is easy to be found. However, the internal loss caused by irreversibility is not easy to be found. In this section, we will discuss the relationship between the work loss and the entropy generation. The work loss in irreversible engine. This picture tells us two engines. One is reversible engine, another one is irreversible engine. For reversible engine, as we know, the QH from the high temperature reservoir, we obtain the heat energy QH into the engine. After engine, there is a little thermal energy QL rejected to the low temperature reservoir. So QH minus QL is WRE. Here, RE means reversible process. Also, we know QL over TL minus QH over TH equals 0. From the Carnot cycle, we obtain this equation because the process is reversible process. On the other hand, for irreversible engine, also by the energy balance, we obtain QH minus QL prime equals W. Here, the W is the actual engine give out the work. Also, in this process, the entropy generation is delta Sg. Delta Sg equals QL prime divide TL minus QH over TH. We know delta Sg always larger than 0. So WRE minus W equals QL prime minus QL. This equation tells us the lost work in irreversible process increases the waste heat to the low temperature reservoir. So delta W equals WRE minus W equals TL delta Sg. Delta Sg is entropy generation. Okay, problem 1, the first law of work loss. In the picture, we know we have two certain states, state 1 and state 2. Export total work loss caused by the irreversible process equals T0 times delta Sg. T0 is the environment temperature. So from the certain state 1 to certain state 2, there are two processes. One is reversible, another one is irreversible. In these two processes, certainly work export is different. The work loss is T0 delta Sg. We can give some calculation. To certain states 1 and 2, the process R is reversible. The export work WR. The heat release to environment is Q0R. we have assumed. Another process I is irreversible. Export work is Wi. Heat release to environment Q0I is another heat energy. In this picture, we assume the system is in perfect environment. Based on the first law in the same initial and final state, we can obtain the work loss equation is WR minus WI is the different process, the work loss. Certainly equals Q0I minus Q0R, means Q0I is larger. Okay, we give another assuming is the irreversibility by the heat transfer between system and surroundings always is produced in the system. The temperature in the boundary is always T0. T0 is a constant. Then the entropy flow entering system in irreversible process I is delta S Q I equals minus Q0 over T0. Here minus means the system lost heat. In reversible process R, because the process is reversible, so the total entropy change is same as the entropy flow, only entropy flow, no entropy generation. So delta S is delta SQR. Delta SQR is entropy flow, always equals minus Q0R over T0. Okay, because entropy is a state parameter, is a property in any condition, no matter how reversible or irreversible, it is same. So delta S equals delta Si equals delta SR, because entropy is a state parameter, is a property. So they are same. Therefore, the work loss difference in two processes, WR minus WI, equals T0 times delta S minus delta SQI. Delta SQI is the entropy flow in irreversible process. So the work loss just is T0 times delta S minus delta SQI in irreversible process. In irreversible process I from state 1 to state 2, the entropy production just is the entropy generation. So delta Sg, it is entropy generation, equals delta S minus delta Sq I. I means irreversible process. Okay, here we can obtain the total work loss in irreversible process. WR minus WI equals T0 times Sg. Delta Sg just is the entropy generation. So this equation can be called the first work loss law. On the other hand, the export work difference between reversible and irreversible process is just the exergy difference, also equals the energy. So the energy WR minus WI equals the exergy difference EXR minus EXI, just same as energy. Energy is just the exergy loss due to the irreversibility, so AN equals T0 delta Sg. We can say this equation also is the first work loss law. Problem 2. The second law of work loss. If in one large process includes many sub-processes which can be separated in the intermediate state. For example, from state 1 to state 2, here is a larger process. However, in this larger process include some sub-processes. For example, 1, 2, 3, 4 include 4 sub-processes. Certainly, these sub-processes can be separated in the intermediate state. In this case, we can calculate the work loss. Okay, the second law of work loss tells us in environment T0, P0, the total export work loss equals the sum of the work loss in each sub-process. At the same time, it also equals the product of the T0 and the total entropy generation. Just as AN equals sigma ANI from I from 1 to N also equals T0 times delta Sg. Here T0 is the environment temperature. Delta Sg is the entropy generation in the irreversible process. Okay, we can do some summary. In environment T0, P0, the total export work loss equals the sum of the work loss in each sub-process. At the meantime, it also equals the product of the T0 and total entropy generation. Just these two equations. Noticeable, delta Sg is the sum of the entropy generation. Okay, problem 3, the third law of work loss. If a total process includes a small irreversible process inside the system, noticeable here the small irreversible process inside the system is not all of the system is irreversible. Only a part of the system there is an irreversible process inside the system. Then it will be produce work loss. Certainly, any irreversible process produce some work loss. Assuming system temperature is T, environment temperature is T0, this small irreversible process will produce an internal work loss, dWi. Noticeable here is internal work loss. Internal work loss is not same as external work loss. Noticeable, please. Okay, for example, here is two processes. One is reversible process, another one is irreversible process. However, in one reversible process, maybe include a small process is irreversible. In this case, internal work loss, dWi R. If it is in an irreversible process, only a part of system include a little irreversible process. The internal work loss is dWi. There are two processes include a little small irreversible process. Certainly, the internal loss difference is dWi R. R means the larger process is reversible. Minus dWi I. Capital I means the larger process is irreversible. Certainly the work loss, just the work difference, equals T dsG. dsG means the entropy generation. T is the temperature of the system. Noticeable, this T is not T0. It's not same as the environment temperature. So here is T dsG. Also equals internal exergy loss. So dsG equals ds minus dqi over T. Okay, here last equation just is the third law of work loss. The last one law of work loss is problem 4, the fourth law of work loss. In a process, if it includes a small irreversible process in local temperature TL, here I give a noticeable is TL, same as the last page, the T. Beside the small process, other process is reversible. So only a small irreversible process. Then this irreversible process will have the internal work loss. The relationship between internal work loss and external work loss due to the internal irreversible process is dWg equals T0 over TL times dWi. Here, dWi is the internal work loss. dWg is external work loss. There is some relationship. So this equation is very important. Please remember it. Here is fourth law of work loss. Okay, thank you very much.